Hi, I'm Stefan, the organizer and host of the embo++, the next level conference for embedded software developers. The talk you're about to watch is about deserialization and serialization of binary data. It was given by Christoph Thurnheer at the embo 2021, and thanks to Leica Geosystems, you can watch this talk online for free.
Deserialization and serialization of binary data. I have a small introduction, error propagation, identifying types, message types, and how to create such messages. I work for Hexagon. Hexagon is quite a big company with a lot of brands. I actually work for Leica Geosystems. We are here in Switzerland, have roughly over 1,300 employees, and we do everything that has to do with measuring stuff. So we measure distances on construction sites, we measure the location of trucks in mining, we measure pipes under the earth. We do some similar stuff like Google Maps, measuring from the rooftop of a car. And I actually work on a machine like this. This is a theodolite that measures points in the field. Such a theodolite measures the distance to such a prism, can be remotely controlled. So you see here the graphical user interface. It has laser beams to track or detect a prism, so you can automatically set the device that it should track such a prism. Therefore, we have motorization in here. So it rotates automatically vertical and horizontal. Therefore, we also need to measure angles in here and how the instrument is tilted. And therefore, we have various microcontrollers and FPGAs in here. And especially these microcontrollers need to communicate to each other. And that's what my talk about. How could we handle such things? We used to also use the famous packed structs, do a reinterpret cast on that, put it on the wire. But probably all of you know the problem is compiler specific extension. The NDNS is machine dependent. So you have to be lucky that everything fits together. If somebody accidentally adds inheritance or something, you also serialize and deserialize that, and you get into problems. There are no compiler errors which would detect such problems. Then in the early 2000s, of course, everything needed to be an object and must have inherited from something. So we also had a serializable interface. You needed to declare your serialize function, and you would get in the correct serializer depending on NDNS, depending on what kind of encoding, decoding you want to do. But also here there are problems. There's inheritance needed, and you need a pure virtual function, so the compiler will force you to provide that serialize function. And especially on microcontrollers, probably some of you already also stumbled into that problem that if you declare a pure virtual function, if you call that in the destructor or a constructor somehow of this object, it will call this pure virtual function in a GCC case. And sometimes this calls, I think, std terminate, or it throws an exception. But in our case, it just through the back door, the whole exception handling came back. Of course, you can also here provide your own implementation, but also then you have to somehow work around stuff, and it's not really so nice. So as a little side note, we used to protect the destructor. That would save us some, in some circumstances, some virtual table pointers. So we could reduce the code size if we would have a lot of messages on our microcontrollers. And then we came up with another solution. So we did it the C++ way. We forced to have a parse function. We hand in the coder as a template argument, and one is then required to declare the variables he wants to have serialized or deserialized. So this is done by a small wrapper class. In the sending case, we need to overload the pipe operator, and this will, in this case, it's the member function. We just call encode over our actual coder implementation. We will return this or an error code if it failed. And we return something like a result of the send coder. And this result here is actually like an implementation of the expected proposal. It can be of a type T or an error code. In our case, it's similar to an STD optional, which either returns the other value or it returns false or null opt, or an STD variant. In our case, it's just returns you the send coder or it returns you an error code. It's quite easy to use. You specify which kind of type you want. You initialize it, you do something, and you can check it if it's valid. If it's valid, it has the value in it. If it's goes to false, you know that's there an error. We implemented that this just will terminate your program when you're accessing the wrong thing without the check. So you will notice immediately. So as we now go back to our event, our parse function, the parse function here, of course, returns a result of a send coder. So we need to also, our send coder needs to implement a friend function, which takes the result send coder and, of course, the type. Then we can call the coder. If the coder is still present, we know that there was no error before. We encode, we return the coder if it's successful. Otherwise, we say there was some sort of an encoding error. And if it already failed on the first glance, we just return the original error. So this will then actually, the whole chain will expand to this magical if block. So if the coder can encode variable A, it's successful, then it can encode B and D, and if everything is successful, we return it's okay. Otherwise, we have an encoding error. And I just noticed there's an error on this slide. So writing such a piping function by yourself, you see humans get confused when the if are too nested. The compiler can do that much better for you. So on the receiving end, we just hand in then here in the template code the receive coder that has the same overload for the receive coder of the pipe operator. It's just calling decode instead of encode. The rest is the same. Of course, it also needs the friend function of the pipe operator. And then you are actually already good to go. It's possible to serialize and also collect all your members. This actually would not be needed if we would finally get reflection within C++. So hopefully one day there will be this reflection available. And also, if this probably don't work. So if we now go here to Godbold. I implemented. I'm sorry for the small thing screen size, but I have here the coder implemented. I have here the encoder implemented with the pipe operators overloaded. I have my small event. I have a static assert that this is really going to go everything in the buffer, and as one can see, there's hardly any code generated, so the compiler is able to optimize everything away. Most things is actually here from the assert, most code. So we are able to have a nice parsing function which actually generates no overhead, which is really nice on small microcontrollers. We don't care as much on our big CPU. But in our instrument, we have very small microcontrollers which control the battery, for example, which only have a couple of kilobytes of flash. There we are quite interested that it's not bloating. So now we are able to serialize and also we have a serialize and deserialize function, which will automatically be generated for us. But of course, on the receiving end, we also want to generate such messages. But how do we create them? Somehow we need to identify the types, different message types, and we would like to know that at compile time. So we just introduced our an identifier. You need a unique ID. So this is actually only a template class which defines a static const ID type, assigns the ID. So we have it present at compile time. Then we are able to declare multiple such events. We can put it in a tuple. So we now have a tuple of all messages we would like to receive and generate. Then we created a called a message factory where you can hand in this tuple as a template argument. And we will now have a look into this message factory, how it will generate those messages for us. So this is done by, we have a public function which will be called by a pre-decoder which decodes the ID, which we encoded before. Then we have an internal creator class which is responsible to create actually these messages. It gets the ID, it gets a channel, and we have a create implementation where we hand over this tuple, and well, let's have a look at this create implementation. So this is quite big functions, as a big function, a specific function. It gets also the tuple with all the messages types. We take the first, declare the rest. Then here we get the ID from the parser. We compare it to the first ID. Then we create the message. We can send it to the channel for decoding and further usage. And if there are, of course, more messages than only one, we have the if const export. If this is the size of the rest is greater 0, it will just run a call create implementation again and do us a recursion of this function. So actually not a really code recursion. Compiler sees through everything. It just will generate a big if-else struct. So as you know, we had the identifier before, so every message of us contains this ID, which we can access here. And then we are here can create all our messages which we declared before. It actually, of course, it's searching for the messages is also the further back it is, the longer it takes to find it. So we would actually implement at the very end something like a ping or getting a version number. And in our case, the first events would be something like the Engel events. I mean, if you remember the machine, these are really frequent update. So they will be treated very fast. So yeah, we have here the header decoder. Go to the message factory, and then we are going to the channel, which is responsible for dispatching the messages and decoding, and of course, if you're sending for encoding the messages. And here's the message factory. So at Leica, we also have just not only events, which are fire and forget. We also want to have commands to set specific things, which we send and reply. There's something like TCP, so your guarantee, also actually you know you should get a reply. If you don't get the reply, something went wrong. And the events are just fire and forget. In our case, the angles are coming at such a high rate that if we would miss one, we don't care. We get the next one. They're time stamped. Then it's not just a problem. But of course, now we have additional problems. We have now two categories of types. And we need somehow to distinguish between them when we are creating them, and we need to distinguish them when we are handing it to the channel, because the channel, in a case of a command, needs to generate a reply. In case of the event, it does not. So we introduced an event type and a command type. So now you actually inherit from an event, give it the ID, or inherit from the command. If it's a command, give it an ID. Now only the IDs need to be unique within the event types or the command types. Have our parse function. So actually this is quite easy. The event C and the command C are the same. They now inherit from the identifier type. So we get the ID again, and we're just using the type tag of an event T, which is an empty struct, just to that we can identify if it's of type event or of type command. And also this will not bloat our first event because these are actually empty classes. There are no members in here, no functions. So so-called empty base class optimization comes into play. So the compiler will not generate anything in terms of size for these two classes. So the size of this class is still the same. Yeah, and here's the identifier. Of course, we have the ID again that the implementation function still works nicely. So now we are able to create events, 1, 2, 3 events. We can now also have a normal command. And we now, the receive message is now, of course, contains the first event, the second event, then the first command, the third event. So we put all in the same tuple. This convenience for the users of the framework. We also hand it just to the message factory. But of course, now inside of the message factory, we need somehow to change our interface. Now, instead of having create message and only one message creator, we now, of course, just instantiate an event creator and a command creator. And of course, we have a create event, create the command. We can also encode this information, of course, in the header, that the header then, if he calls it, knows which kind of function it needs to call. Hands in the ID and again the channel. But of course, we somehow, I've got some mention here. The creator gets all events for the event creation and all commands for the commands. So we need somehow to filter that first because we get only the tuple with the according types. So we generated a small helper function isEvent. So if it is same as event type, which we declared or the type T, then it is an event. The same for a command. If it's of type T and command T are the same, it is a command. We put it in a filter, and then we get here a tuple back of all events and of all commands. So we have here our small filter. If it is of type, so if the class E is of that type, so it's a template of bool. If it's true, we just return the tuple with the template E. If we have a specialization for false, so if it's not of that, we just return an empty tuple. So you put in the predicate for the filter, you put in the predicate and the sequence. So it's overloaded for tuples. So we accept the predicate and the list of types. So the tuple with the types. We check if the type also if the predicate evaluates to true, it's of that type, and we can concatenate the tuple again, and so we are able to filter our events and commands.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leica habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
So here we are just going to the type. This is the type definition of event T, which we used. So we now know this first event is of type, is an event type. So that's how it works. We have the all events, we have the filtered command. Now we are able to really pass in the correct tuple with the correct types to our creator. We have again the implementation. So now the next problem is, of course, if we are sending it to the channel, we also need to distinguish if it's a command or an event. This is fairly straightforward. So we have a function sent to channel. We enable if it's of an event, we can reuse our predicate here. We will return the error code. If it's true, then we can say call channel receive event, and if it's a command, we will just call the receive command. Okay, now we are able to serialize and deserialize objects. Also, we are able to create them, but probably many of you saw that we just said we're making unique. So we would need to go to the heap. On small microcontrollers, normally you don't want to use heap, at least we don't. So we need to get rid of this make unique. We do that by implementing a policy, and either an in-place allocation policy or a dynamic allocation policy, because we want to use the heap on the big CPU because it has enough memory and enough calculation power. And of course, on the microcontroller, we want to be able to create the messages on the stack. So we introduce this Boolean use static memory. If it's true, we take the in-place allocation policy. If it's false, we can use the dynamic allocation policy. Then our creator now will inherit from either of these policies, depending on which is allowed to use. We then now introduce a new interface. Also, it's actually only the allocate message function which needs to be implemented in both. Now we can create our message with allocate message. We even could return a result, check if it's a message, send it to the channel, or return an error. So of course, the dynamic allocation policy is quite easy. It's still a unique pointer of that message type. We return make unique message. It goes to the heap. Everything is fine for the CPU. Now the more interesting part, the in-place allocation policy. The in-place allocation policy also takes all the types, which has. We use the aligned union of all messages. Aligned union will guarantee us aligned storage for the biggest type of this type list. We can use that type as a storage. We then also need, of course, a in-place deleter, which then will delete our object if it's destroyed again. We now declare our unique pointer to be of message and in-place deleter, and our allocate message function will allocate the message on the storage, interpret, cast it, put in the deleter, and hand it over to the user. Of course, because my slides are not so big for code, there's also some memory protection, like we need to know if the storage is free, so we need somehow to protect it. I put that out of the slide because of size reasons. So also here we could then, if the storage is already occupied, return an error code. So we would then have a result type of this unique pointer. Okay. So the conclusion now, we have the possibility to create all the events. We can create several events and commands. We put it into the tuple. We instantiate a channel. We instantiate the message factory with the received messages. False for dynamic memory, true for static memory. Instantiate the factory, hand in the channel, and we are good to go. So let's try again. I see there are already some questions. Did you measure that the later ones are actually later? The compiler might transform the if structure into a switch. No, actually, I did not. That's a good point and a very interesting point. I'll take a note and I'll try that. This is interesting. Thanks, Paul, for that comment. And okay, there are not any further questions. And I would like to share also the Godbolt link. View. So did here really copied our implementation to Godbolt. So we have the is type, we have the filter, we have the in-place allocation policy here, we have the dynamic allocation policy. We have our event type, command type. Our ID type is of type short. We have the identifier. We have the event. We have the command. We have our message factory. Now, of course, you also see that it's actually the specialization for tuples. I added a channel type here that I can put in a custom channel. Here's the complete implementation. And you also can see already here, there's not as much code generated. Actually, you see it already here. Funny thing is Clang actually generates quite some code, but the most of it is also from static asserts. Then we have our coder. And just this is a quick and dirty coder implementation. Please don't reuse it because it only works with jars. As you can see here, if you would insert anything else than something that's more than a byte, you will lose information. You have encode, decode function. We have a specialization for the array. We have our receive coder. And we have here our magic first event. It contains 1, 3, 4, 2, 1, G, and 3. We create our receive event. We have the channel. This is I used here a specialization for receiving event for the first message that I am able to actually copy it and have a member, which then I can check here. So I instantiate the buffer, of course, with a super name. It's the embo IO. We have the channel, the message factory. Then we call create event with the number 1. We expect it that it's embo in there. And then we do assertion on everything that it is actually parsed correctly. Because if it would be default initialized, the one, then we would have gotten 1, 3, 4, 2 gibberish as 1, G3. So it works. And this version, and actually, as the compiler can see through everything, it's quite nice. It's a low memory footprint for our microcontrollers. We can use it on both sides. On the CPU and on the microcontrollers, we don't need to duplicate the framework or the code. And we have a nice small implementation of creating messages. We are able to pass error codes through, and yeah, it has low memory footprint. So also Leica is on various platforms. If you're interested in our products, follow us, and yeah, I will be then open for questions. So currently I do not see any questions. Maybe I missed one. Okay, then thank you for your interest in my talk. Hope to see you somewhere at the conference, speak to you, and enjoy the rest of this awesome conference.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.